to look at a couple examples here of these E2 reactions. The first one that I want to look at is this. So let's put a PR stands for a propyl group. Let's put a propyl here, and then 1, 2, 3. And here we're going to put 2 H's, so an H. So an H here, and an H here. And then let's throw an iodo group up here at the top. So here's the iodo group. And then over here, there's a CH3 here, but let's draw this out so we're real specific about what's getting lost here. So there's an H that's on a wedge here, and an H that's on a dash here. All right. So looking at this thing, we have a beta position on both sides here. So let's label some stuff. So here's your alpha position, right? And then let's call this, how about beta 1 and beta 2. And then let's make a little note down here because I want to show you a trend. So here at beta 2, right, we have 2 H atoms. So that's important to note. 2 H atoms are there. And then here at beta 1, we have 3 H atoms. All right, so what we're going to look at is really 3 cases. When the beta position has 2 H atoms, 3 H atoms, and then when it has 1 H atom. So let's take a look at this first position, at the beta 1 position. So we're going to come over here, and then let's look at the E2 at beta 1. And then we'll use here hydroxide. So what's going to happen is hydroxide is going to come in and take off one of these H's. So which H is going to be lost? Well, remember here that this iodide is leaving. It's on a wedge. So if we're in a wedge right here, then we need to take off an H that's on a dash, right? Because remember, this wedge dash relationship gives us an anti-coplanar arrangement, and that's required for the E2. Okay, so specifically that H is going to be taken. So what we're going to do is we're going to swing around and we're going to draw an arrow here to that H, and then these electrons are going to swing around and make a double bond right here, and then we're going to kick off the iodo group there. So let's take a look at what our product is. So here we'll have our propyl group. That's going to be our CH2. That's this beta 2 position. Right? We're going to connect up here to where the iodo group was, and we're going to have a double bond down here just like so. So that's our product. So just to point out to you guys here, look, we have 3 H atoms, and it leads us to an alkene with no cis trans isomerism. Right? It's a CH, a terminal CH2, so you can't have cis and trans there. So the take-home message here is we don't have to worry about cis and trans if we have a CH3. So we're not going to worry about it. Well, we might have to be concerned with the 2H situation. So I'm going to rewrite this here down below. All right, so let's take a look at this guy down here. So now we want to look at this reaction at the beta 2 position. So we're going to come over here, and let's do the E2 at beta 2. Same deal. We'll use hydroxide. So in this orientation that we have right now, remember the H is on, or the iodo group is on a wedge, so the H that's going to be lost is this guy right here. So we're going to swing around and we're going to grab this H. Electrons come down like this, and we're going to kick off the iodo group. All right, so let's see what we get. So we're going to have our propyl group here connected down to this carbon. right? That's the carbon at beta 2. The H that's on a wedge is going to come in plane. It's going to be right here. And then we're going to have a carbon-carbon double bond here, and that's connected then to a CH3. So that would give us this as our product, right? Now, remember, we have free rotation around this alpha to this beta 2 position. So something else that we could do here, and I'm just going to draw a little line here, and let's take a look at this, and we're going to do a rotation. So what we can do is we can start off with our structure like this. Here's our CH3 down here at the end. We'll leave the iota group put, so we're going to put the iota group there. And this carbon right here, I'm going to rotate it around. And what I want to do is I want to take this H that's here, and let's see if I can get my highlighter. I want to take that H and I want to move it to this back position. So when I do that, that H is going to be on a dash. This H is going to come around here and be in plane, and that purple group is going to come out here and be on a wedge. We're just going to do that as a rotation. So we're still going to have this tetrahedral looking carbon, right? That's not going to change. But now our H atom will come here. You'll have an H in plane over here, and then your propyl group will come down here. And look, in this orientation, as we go through and do this, and we're still looking here at beta 2. So this is still E2 at beta 2. And we'll use hydroxide again, right? What's going to happen here is that's going to swing around and grab this H. So that H right there is still anti-coplanar with the iota group. It's going to grab that H, double bond comes here, and then we're going to kick off the iota. So what that's going to give us for our product in this case is this. So H is still in plane. That propyl group is going to get pushed back into the plane. And then we're going to have our carbon-carbon double bond and our methyl group there. So when we look at this, we have a situation, right? If we look over here and put our H in here, this is essentially the trans product, and this is the cis product. So in this case, we get them both. We get cis and trans, right? Both our trans and our cis product are formed. So there's another little shortcut that we can kind of remember here. So let's take a little bullet from here, right? That's the beta 2 with 2 H's. That's this situation. What we're going to get is trans and cis. Okay, so 3 H's, don't have to worry about it. 2 H's, we get cis and trans. And what about 1 H? So I'm going to come over here and let's take a look at another example here. Let's look at what happens when we put in 1 hydrogen at that position. So we'll start off here. Let's put a propyl group. Let's come down, up. Make this the iota group here, just like we did before. Clean it up a little bit. And then over on this side, I'm going to put a methyl and a methyl and a methyl. And then here, we're going to throw in a methyl group and then an H right now. All right, so here's my alpha position. Here's my beta position. All right, and I want to point out to you down here is that our beta position, right, has only 1 hydrogen. So with 1 hydrogen, we're going to have to be a little careful. And so our H that's going to be lost right here is on a dash. It's where we want it. If it wasn't, we'd have to do a rotation to get it to be on that dash position, right? So looking at that here and looking at this here, we're only going to get 1 product. So our hydroxide group is here. We're going to swing around and grab this H, right? That H will then, the electrons there will give us our double bond, and then we'll kick off our leaving group. So here our propyl group hangs out up here. We're coming down to our carbon at that beta position. That methyl comes in plane, double bond, and then over here we have our T-butyl group. That's it. That's the only product we get. So we only get, in this case, cis or trans. We can't get them both. Right? So in other words, the propyl and the methyl group cannot be interchanged here. So as an exercise, what you ought to do is try to carry out the same reaction, but on a piece of paper, switch this methyl group and this H group with each other. Switch them, and then see what you get. What you'll get as your product is these groups interchanged with each other. Okay, but you'd only get that. Now this idea of wedge-dash relationship that we saw in these linear structures also applies to cyclic structures too. So let's take a look at a ring. So for this ring, I'm going to be very specific in what I put on here. So let's take this position and let's make that an H atom. And then I want to put here a CH3. And on this atom, I want to throw in a leaving group. So let's put an iodo group there. And then over here, I want these to be 2 H's. All right. And then here's what the reaction would look like. We're going to go through here, and we're going to use CH3O-. And I want to look at E2 for this. So as we go through and learn more, we might discover that this has some competing reactions along with it. Now remember, we have to have this anti-coplanar or anti-paraplanar arrangement, or a wedge-dash relationship is what we said before. So if we take this, how do we know that we have an anti-arrangement between the leaving group and the H that's being taken off? So what we're going to do is we're going to take a look at this, and we're going to draw some chair stuff. So we're going to come through and we're going to look at it this way. Right, so here's our chair. And what I want to do is I want to take, for the sake of making this a little easier, I want to take that position, that blue position right there, and I want that to be right here. And I'm going to kind of take it and I'm going to rotate it on its side, and I'm going to put it in an orientation that puts my CH3 group pointing down right here. So that's where this is. Right, that would make this H go to this position. So remember, as we go around the ring, the next atom's going to come up. That atom would come out like this. And the CH3 and the I group are on different faces of the ring. So my iodine is now going to be up here. Right, and that's our H that's right there. So that took care of this little bulleted point. Now we're going to come around to this one here. That's going to have an H that's pointing down right now, and one that's coming out equatorial right here. And we know that the orientation here needs to be anti. We have to be anti. So when we look at this, the iodo group is pointing up right now. This is pointing down. These are anti to each other. So this here, coming around here, these are anti. But it doesn't have an H. The H is not there, right? If we look over here, these are anti to each other, and obviously we got an H right there. So there's no orientation that we can put this in where we have an axial relationship and we're anti to each other. So this is called transdiaxial. So the requirement in rings are called transdiaxial. And again, this is not that hard because look, all we're looking for here is a wedge dash relationship between the leaving group, right, or in this case the iodo group, and the H. So because this is over here on a wedge, we can't lose that H. So in this case, the only H that's left is this guy. That's the only one that has the potential to undergo an E2. So reaction-wise, this is going to swing around and it's going to grab that particular H, double bond, kick off our leaving group. This is a real common type of question to show up on standardized tests. It's testing to see whether or not you remember the stereochemical requirement for carrying out this reaction. So in this case, that's your only product. So let's just make a careful note here. This is your only E2 product here. So just be cautious of that as you guys go through and you start looking at E2 reactions that involve rings.